Hey guys, this is Yoru. In the last lecture, we have learned about the concept of Cartesian coordinate and how to use coordinate transformation to describe the position of a point on a rigid body. In this lecture, we will show you how to apply coordinate transformation to derive the constraint equations for Revolute Joint. First of all, what is Revolute Joint? Revolute joint is a kinematic pair that connect two rigid bodies. The rigid bodies connected by a revolute joint will not be able to translate freely, but they can still rotate around the rotation axis, just like the picture here. The video here shows how a 4-bar linkage system with 4 revolute joints works. You can see that the only allowed motion between bar 1 and bar 2 is rotation, and the fact that the revolute joint connects bar 1 and bar 2 so that the connection between bar 1 and bar 2 will never break. We can also find a lot of applications with revolute joints. For example, on the robot arm shown here, you can see that there are 3 revolute joints. These revolute joints allows the robot arm to pick up things in a way similar to human. Now let's recall the material we mentioned in the first lecture. We learned that the revolute joint will reduce 2 degrees of freedom, which means it will provide 2 constraint equations. So in the following slides, we will teach you how to derive the constraint equations for a revolute joint. To do so, we need to rely on the geometrical properties of revolute joint. That is, the revolute joint makes a point P1 on rigid body 1 and a point P2 on rigid body 2 share the same location. We say point P, which means P1 and P2 will have the same position no matter how the rigid bodies rotates. Also, since P1 and P2 are fixed points on rigid body 1 and 2 respectively, their local position vector S1P and S2P will never change. Therefore, we can use coordinate transformation to obtain their position. For P1, the position P1x, P1y is equal to xc1, yc1 plus the local vector S1P. And since it is a local vector in local coordinates of rigid body 1, you need to times the rotation matrix with theta 1. For P2, the position P2x, P2y is equal to xc2, yc2 plus the local vector S2p. And again times the rotation matrix with theta 2. Since P1 and P2 share the same location, we know that P1 equals to P2. So we can get this equation. And if we move everything to the left-hand side, we can get the equation like this. And if we expand the result, we will get 2 equations. These 2 equations are the revolute joint constraint equations we want. So this is how we derive the constraint equations for a revolute joint. Make sure you understand everything in this lecture. It is the first step of CAD for mechanism. In the next video, you will learn how to derive the constraint equations for a translational joint. See you next time.